Welcome to episode 3 of yet another machine learning reading group. Oh, we're gonna do a quick round table of intros. Josh, who is gonna give a talk about Apple Intelligence and how to blah blah blah, something about LLMs and on device. It's a very complicated title, so I'll let him explain.
I think everyone here knows me. I'm Josh. I'm a machine learning engineer at the moment, working in biotech. But I really want to start kind of writing more blog posts to explore like interesting things I see in ML that I don't fully understand and use it as like writing blog posts as a way to like hold myself accountable and like document the process. So Apple Intelligence kind of got announced a couple of weeks ago, so I thought that would be like a great first one to do, just like really try and dive into it. And yeah, this is this first collection of stuff I've researched. So that's the plan here. Cool. I'm going to pass it off to specific people. Arjan, you want to go?
Yeah, I'm Arjun. I'm working at a neuroscience lab at UCL.
Hi everyone, I'm Neil. I'm currently a senior product manager at Elliptic, but I just quit my job and I'm going to join Antler in September to try and start a company. And I'm looking forward to Josh telling Rory how Apple are building Apple things.
Rory?
I feel like that's my segue. I'm Rory. I work at Apple in cybersecurity with a touch of ML, but I think I'm going to get schooled today by what Josh has to say. So I'm looking forward to it. I will hand off to Ben.
Yeah, I'm Ben from Edinburgh. Did my master's in AI there. I'm currently working for Capita as an AI engineer, doing a lot of stuff with LLMs and RAG. And before that, I was at Bank of America, doing a lot of work with generative models, synthetic data, that sort of thing. Oh, I've also got an app which I released recently called Lifey.
Come on,
If
bro.
you
We
want
can't be
to-
advertising.
I'll send a link in the chat if anyone's interested.
Can you choose someone else to pass to, Ben?
Yeah, Jamie, have you been?
Hi,
Jay?
I'm Jamie. I've worked in tech, data science, data engineering, doing machine learning for just over 10 years. Companies like Candy Crush, so King, and Apple. I'm leaving my job at TikTok this week. I'll pass over to James.
Oh, hey everyone. I'm James, currently working as a product manager at Causal Lens. So a lot about around causality, causal inference, etc. Admittedly a product manager, so not as technical as you lovely people, but that's exactly why I'm here. So wonderful. Who else hasn't been? Dan? He's been?
Yep. I'm Dan. I'm a machine learning engineer at Early Birds. I didn't join you guys in Edinburgh, but I studied AI in Amsterdam. So if any of you guys are from Amsterdam, it'd be very cool. And I'll pass it to Callum.
Hey everyone, thanks Dan. My name's Callum. I am a research engineer at InstaDeep, where I work on kind of multi-agent reinforcement learning problems, specifically around offline data, and shortly moving to London, currently in Cape Town. And stoked to be here. I don't know who has not gone, but maybe Oshin, have you gone?
Yeah,
I haven't gone. Hi everyone, I'm Oshin. I'm from Dublin, Ireland. Currently doing a PhD in machine learning signal processing in Eindhoven in the Netherlands. Working on machine learning signal processing for medical imaging. And looking forward to Josh's talk. Who else hasn't gone? David, have you gone?
I think David and Niels. Start with David.
Okay. I'm David, background in AI, currently building a startup, and also joining EF in a month, focusing on defensive and AI technologies. And who's it? Niels?
Niels.
Yeah, thanks, David. Yes, I'm doing a PhD at UCL, studied at ETH. I'm working mostly with generative models for time series. And I was curious. A friend liked the post from Maria and wanted to see what's up. So back to you, Maria. Thanks for this.
Thanks, Niels. Nice to have you here. Basically, most of us studied a Masters of AI in Edinburgh, and then, we all went to do our own separate things. Also, a quick intro from me. I have been a data engineer for the past 4 years, mostly in the crypto compliance world with Neil, and I also just quit my job, and I'm gonna do EF from September onwards. And in the meantime, I'm also going to do a shameless plug and share my webpage. All yours, Josh.
Thanks for the fireworks, Maria. Cool. Okay, so some quick background. So for people that have joined previous talks, Oshin and Callum presented. They're both very active in the research space. and they kind of presented their own research in a lot of detail. My talk's a little bit different in that it was done as a motivation to try and explore an area that I wasn't super familiar with. So I would say the depth of the talk is probably going to be a lot less than theirs, but the breadth should be, I think, a little bit wider. So we're going to be short on time, so I'm going to be skipping over a few things. I picked some components to go more into detail on, which I think will be more interesting for like an ML crowd. But I wanted to really try to highlight the whole end-to-end process of building an LLM that's designed to run on devices, on iPhones. So I'm just gonna get into it. So we've got maybe that a little bit smaller. So I'm going to go through an intro. We're going to do pre-training, post-training, touching on group query attention, adapters, LoRa stuff, and then compression and quantization at the end. And the kind of goal is for it to kind of mimic the stages you go through, or the stages that Apple went through to develop their on-device LLM. So a lot of the information I use to kind of like put this talk together is from their. They released a blog post that had some kind of like vague details. I was originally using that and kind of trying to see what they kind of were pointing towards, and then reading the papers they were referencing and trying to get an idea. And then annoyingly, like a few days ago, they just released that big, like 47-page technical report. So I had to go through and like rewrite all my stuff because they actually provided a lot more information there. So I'm not doing referencing properly on all the pages. This is kind of a tool I put together quite quickly. But all of this is going into a blog post that I'm going to put on Medium, which will be much more comprehensive and in-depth. This talk is going to be, I'm just going to be conscious of time. There's a lot of areas to go through, so it's going to be a little bit more high level, and I will skip over some of the stuff that there's some assumed background knowledge, which I don't think should be too much of an issue. Cool. So for some context, Apple Intelligence is a suite of generative AI models. So they have like some diffusion models in there, some LLM stuff in different varieties. I'm really just focusing here on the 3 billion parameter LLM foundation model that runs on device. So they have some server models, they have some offloading to ChatGPT. I'm not really touching on any of that. And they don't really release much information on their diffusion models, which I think also do run on device, but yeah, there's not much information there, so I'm not going to talk about those too much. And yeah, these models are designed to run on iPhones. So obviously a very resource restricted device. You don't have a lot of battery power. You can't kind of you don't have a lot of memory, so there's a lot of stuff you need to adapt from around that. And then I think this is an interesting project to look at, because this will probably become the most widely used LLM on the planet. I don't know, but definitely on device. I guess ChatGPT will probably end up being, I don't know. It's going to be hugely used, very impactful to probably a lot of people. And Apple, interestingly, kind of like marketing this as AI for the rest of us. So I think it's for the people that aren't using ChatGPT and stuff like that. That's what this model is designed for. Cool. So very quickly, this the model is called AFM, Apple Foundation Model, and AFM on device is the one I'm talking about here. They have one that's a server model, but we don't care about that one. So AFM on device is a decoder-only transformer. I assume everyone's familiar with transformers. It's pretty standard for language modeling stuff, so I'm not going to get into it. And interestingly, they've been very transparent with a lot of the configurations and hyperparameters they use to create the models. So we have, in the paper, they released kind of their model dimension, the exact size of the model. It's quite interesting, but not super relevant for this talk, to be honest. Okay, so jumping into pre-training. So you have this model, which is a transformer decoder, initialized with these kind of this many blocks and dimensions in the heads and query heads, a number of layers. So what you want to do is a model like initialized from scratch. You want to first do a pre-training phase. Are you guys able to see the text on the slides? I see Arjan squinting an unusual amount. Okay. Cool. So the goal of pre-training is to instill basic concepts of language. So in LLM training, pre-training and post-training. The goal of pre-training is to get a model that kind of understands how to speak English and loads of other languages as well now. Models are really good at being multilingual. They're good at coding, they're good at writing and math, which I guess are forms of other languages. So that's the goal of pre-training, just instilling a lot of information into the model. And then post-training is more about aligning the model with what you want it to do and how you want it to respond to users and be a useful assistant. So the sources for, I'm going to skip through a lot of this stuff to do with pre-training and post-training. It's very high level, it's not really mathsy, it's not super fun. And then we'll go slower a little bit on some of the later stuff that's a little bit more technical. So they license a lot of data, they have open source databases. data sets. They use Applebot, which is like an internal web crawler tool that I assume the Apple boys here might know and interacted with. They really throughout the whole report really emphasize the quality of data over the quantity. Really, like in every section, pretty much when they talk about data, they say that they put so much work into really clean the data, and will choose to disregard data and throw it away rather than include potentially data that they can't validate the authenticity of or how noisy it is. The tokenizer is pretty standard as well. It's by-pair encoding. Shout out to Edinburgh. And there are one interesting quirk of the tokenizer that I just wanted to highlight is that they split their numbers into individual digits, which is different to what GPT-2 tokenizer does, which kind of learns tokens for common numbers. So like the number 10,000 would have a token assigned to it. Whereas in this case, they kind of they point this out. I don't know how other modern tokenizers do this, but there was a blog post I shared recently in our Edinburgh chat that was talking about GPT-2's tokenizer and how it's kind of learning all this interesting stuff to do with integer tokenization. Interestingly enough, the Apple don't do that. They just split everything into individual digits. And the total vocab size is 49K. Again, pretty standard. Cool. So the pre-training recipe, essentially you have 3 steps of pre-training. First is the core, and this uses the majority of the computational budget. So what this does is just standard next token prediction. It uses all the data they have, open source data sets, data crawled from the web, licensed data, all of that's written in there. That's kind of, I think in the paper they say it's about 80 to 85% of the compute budget is used for that. Then you have the next phase is continued. This is when you downweight lower quality data, and they raise the influence of high quality data sources to do stuff like code, math, and their licensed data, which comes from publishers, which I guess expect to be slightly higher quality than Reddit comments, surprisingly. Okay, and then you have context lengthening is the phase after that. So I think this is around like 5 to 10% of the compute budget, maybe like 5% of the compute budget. And this is the final stage of pre-training, and they heavily prioritize longer sequences in this data set. So the idea is to get the model to learn longer context, contextual understanding, and then all of these stages use kind of weight decay and float 32 or float 16 kind of representation store parameters, which will be important later. The model is distilled. The FM on device is distilled from a server model, which is just a bigger model. So instead of initializing weights from scratch, they distill it from a model that's slightly bigger that they train. And then AFM server is trained from scratch. Okay, now it's going to get a little bit. I'll slow down a little bit. There's a couple of things to touch on here. So post-training. So now we have this pre-trained model that we assume kind of understands basic concepts of language. It can complete text for you, but it's not really it's not that useful of a model. So post-training is kind of the process of aligning the model with what I guess Apple desire for the model to achieve for them. And there's 2 main stages. So first, you just have regular supervised fine-tuning. This is where you have a data set of kind of prompt inputs and desired responses that the model should kind of do for these tasks. This is very simple, so we're not going to touch on that too much. The more interesting stuff is the RLHF stuff they put together, and they actually claim to come up with 2 novel training algorithms. But from what I've seen of these algorithms, they seem to be combinations of prior algorithms, and it's not super new stuff. It's more the combination of existing stuff into one kind of common framework or one package. But the 2 algorithms they highlight a lot in their technical report is one's called ITEC, and then this is MD-LU, which we'll start with ITEC and then we'll come to the other one. So supervised fine tuning. I'm really not going to speak too much about this, but you just collect data. You have label data, so input output examples that are good that it goes through. They do some synthetic data here, which is interesting, but the RLHS stuff's a little bit more important, I would say. Cool. Okay, so are there any questions up until now? I know it's a very quick breeze through. It's more just kind of a background. I think everyone's pretty familiar with pre-training stuff. If anyone does have a question, just raise your hand, and then kind of after each slide, maybe I'll see if there's any questions and we can dive in. So ITEC, this is more of a framework rather than specific RLHF components. But the goal with this algorithm is to have an iterative framework that allows you to continually refine your model. So I'm going to go through the steps of the algorithm. I've kind of really, they go a lot more detail in the technical report. I've just abstracted away the core operations of each of these steps. What's the core objective they want? So you would start with a pre-trained model. This can be the output from your pre-training phase, or it can be a previous iteration of the iTech algorithm. And you take this model, and what you do is you'd start to collect human preferences. Let me just go on notes over here. Yeah, so you collect human preferences where annotators would kind of look through two responses and they would select of the two which is their favorite, and they would add some qualitative metrics to that as well. So also rating on metrics such as truthfulness, safety, and they have kind of like a slider where they can convey exactly their preference for the model. So one can be this response is slightly better, or this response is significantly better. All this data is kind of tracked and used to train the models. And then what you do is you gather this data, this human preferences, and you train a reward model. The goal of the reward model is to, given a response, a prompt and a response pair, predict what the human preference is going to be on that. So it's a model that learns to understand kind of if a given prompt response is going to be good or bad, essentially. Then the next stage, let's see, go here, is a fine-tuning stage. So what you're doing here is you're making several copies of the pre-trained model. Yes, Ben.
Hey, sorry, I've got a question about the previous slide.
Yeah.
Yeah. So for the reward model,
yeah,
like, is that just is the text just embedded and then that's just put through a neural network, or like how does that work? What's the input and like what's the output is, I'm guessing, the probability of selecting this one over this one. But
yeah.
like what do they do anything to the input, or?
They really kind of don't provide too many details on the actual implementation of the reward model. They just say the parameters it takes. So it just takes a prompt and a single response. And then you'd run this twice for both responses, and then they would output some sort of probability or some sort of metric that you're comparing.
Okay.
I would assume there's got to be some sort of sequential understanding in that, but they really provide very little details. Yeah, I have it a little bit later on, but I think it would be some sort of model that takes in two sequences and outputs a singular value, a singular predicted reward. Cool.
Yeah, they have. I think they have the responses like significantly better, better, slightly better, negligibly better, or rejected.
Yeah. So that's the data for the annotations. That's how they kind of they grade it. But the way they reference their reward model, like here in the equations, it's only taking in two parameters. So it's only taking in the prompt and a singular response, not two responses to evaluate them. So yeah, I'm not sure exactly. I think there's got to be just kind of comparing some sort of single output, whichever scores highest. Okay, so then then what you do, so you have this trained reward model, and you want to fine tune multiple copies of your pre-trained model. So again, this part they kind of gloss over a lot of the details. I don't think it's super important. They really want to emphasize the framework they use rather than the specifics. But the idea is you have this pre-trained model that you accept at the beginning, and then you fine tune it using different algorithms. So rejection sampling is one where you kind of just generate multiple candidate responses from the model, pass each of those responses through to the reward model, whichever scores the highest is the answer you accept. And then they have a couple of RLE stuff here that I'm not super, didn't dive super into. I don't think it's that important, but essentially these other policy optimizations are kind of tuning the parameters of the model in some way to maximize the output from the reward model. And then yeah, you end up with so they give these three examples in the paper, but they say that they actually use way more in the actual implementation. So what you end up with is a committee. So this committee is a series of these fine-tuned models, and they're all slightly different. And then what you do is you query the committee as a whole. So for each prompt, you sample responses from all of the models that have been fine-tuned in slightly different ways from the committee, and then you select the response that scores the highest from your reward model. And then what you do is you take these. Yes, Maria.
Is this similar to how ensemble algorithms work?
Yeah, I guess it a little bit. So the goal is that having models that are trained in slightly different ways that can give different answers. And I guess some models will excel at different tasks and some will excel at others. I think they actually give some good examples in the paper where they say that they found the rejection sampling models to perform better at instruction following. And then the policy optimization models just were a little bit better at just producing high quality outputs. So for some, so I guess if they included the model, there would be some cases where that model would excel over the rest of the committee. But the idea is, you have this kind of like this collection of models together, and you just take the best for each prompt. You just take the best of all these models. So,
Josh, is this the reward model which has been used in RLHF, or do they have different reward models? One for the committee and one which was used by doing the RLHF stuff.
So this is the RLHF reward reward model you still use.
So you used it twice, once to create basically the samples, and then the second when, for example, in DPO, you don't use the reward model, but then you use the same reward model again.
Yeah.
Okay.
So you're using the same reward model, and then you're refining it through iterations of this algorithm. So what you do here is you then you take the reward model, use that to find the best responses from the committee from any singular input prompt, and you create a new data set, which is all going to be synthetic data that kind of tells you there's this collection of good responses from the committee. You create that, and then you train the original model again. So you kind of discard these pre-trained variants. You train the original model for further iterations using this new data set, using standard SFT, supervised fine tuning. And then what you can do is they run this this post-training cycle multiple times, and they keep running it iteratively, upgrading the model until performance gains start to saturate. Yes, Ben.
Right. So wait, sorry, could you just go back? Maybe David just asked this, but I've still just got a question about the committee thing. So you have a committee of fine-tuned models. These are what the language model that you trained originally. They're being fine-tuned.
Yeah. So you have a singular pre-trained model that comes in. So this, for the first iteration, this will just be the output of your pre-training step, and then at the committee stage, you fine-tune models using slightly different strategies.
Oh, right. Okay.
And then you end up with like variants of the original model that have all been tuned in slightly different ways. And then you get a sample from the committee as a whole, where each of them produces a candidate response, and then you just select the response that maximizes the reward.
Okay. So like, say you separate the original model into like 10 different models, do you then train each one with just one strategy?
Yeah.
And then just keep repeating this?
Yeah, they only kind of use these. They mentioned these 3 examples here. Really, they only describe rejection sampling in detail. They don't describe DPO or IPO too much. So I'm not super familiar on these algorithms anyway, let alone how they use them in the context of this. But they do say that they use multiple others that they don't really mention. And then the problem with the technical report is that it's I guess it's designed to be a product, right? So they sometimes omit some of the details that I think probably end up having a big impact on the final performance. So yeah, you have this committee, you have this data set, you do this stage of fine tuning, and then you run this all the way again, and you start step 1 again with this new fine tune model, and you just keep doing this until performance gains start to saturate. So then you collect some new human preferences, update the reward model, generate responses, select the best, and then distill this into a singular model. Cool. Okay, so that's the kind of framework, and then I'm going to touch on the MD-LU algorithm that they propose as well. Some of this gets pretty heavy, and it's still stuff that is kind of I'm actively researching. So I'm going to just touch on the stuff that's a little bit high level. But I guess in my blog post, I'm going to dive into it a lot more, and there'll be some more like nitty-gritty details there. This is how they frame their RLHF objective. So the goal is you are trying to find the parameters that maximize the expected return of this this expression here, where D is your data set, X is a prompt sampled from the data set, and then Y is a response sampled from your current policy. So I know we have Callum here, who's obviously a lot more of a RL expert. So if he has anything that he wants to add, feel free to jump in. But I'm just gonna go through it in my way of kind of a novice in RL, and feel free to jump in if there's anything I'm saying wrong, Callum. So you're looking to maximize your parameters here. Then what you do is you have your reward function. Just measures how good a prompt is, response is given a prompt. So this is how they always reference it. So it's always with a singular response, and it's not kind of two candidate responses and selecting one over the other or doing some sort of probability. It's always just these two here, which must be outputting a singular value. And then what you do is you want to weight that reward by a KL divergence between the current policy and a reference policy. So KL divergence is just a way to kind of quantify how similar two distributions are. So what you do in this case is the KL divergence would be higher if the distributions start to deviate from each other. And then you have a coefficient here that you use to kind of manage the impact of the KL divergence. So what is on the next slide. Yeah, I think what we can do is, so they then go to simplify this equation to just be the reward, and then this kind of like different flavor of the KL divergence where it's just for a singular sample, and this is kind of the final reward that they optimize for. And just quickly, so you have this is the policy here. Can you guys see my mouse on the screen? Yeah. So this is the policy that you're learning, and what you're trying to keep that policy close to is this reference policy. And the reference policy is always initialized as the original pre-trained kind of policy before you start doing RL HF stuff. So the idea is that you want to learn a policy that is close to your original configuration, to your initial starting point, but is slightly better and moves closer towards stronger rewards. And they say they do this. They say this is like absolutely critical for training the model. Otherwise, it starts to collapse and lose a lot of the initial pre-training information it has stored in its weights. So this term is used as a stability term to make sure that you're maintaining that pre-trained information and not moving too much into a kind of a weird landscape where potentially like the reward model is being maximized, but your kind of the information stored in the model is kind of collapsing and disappearing. Cool. Okay. And that's just same here. Dan.
Yeah. Do you know how they can get the reward model to output a singular value based on also one output prompt? If the labelers are labeling between two, at least that's what I'm expecting that they're doing, right? One versus the other. What is the input here?
Yeah, so it's always two. I'm not 100% sure. They don't specify this at all. I don't know if that's maybe common in LLMs, so they choose to omit it. But I would assume that you are kind of just for each response, you can kind of predict its reward against the average kind of other competitor. So I think you could probably learn a reward model that can just take in a single. Essentially, you're trying to predict the alignment of how humans kind of prefer that response. So I think there are common traits you can learn, even though you're only taking a singular response in rather than a comparison.
Okay.
But yeah, it's not super clear on the paper either. Ben, yeah.
Yeah. So the policies here are essentially like the models, right? Like you get the input as a prompt and the output is text. Or I'm like trying to work out like what the equation in pink like means and how you can have like a KL divergence between. Yeah, do you know what the current policy and reference policy are? Like what the
so the policy is the distribution of, let me see, I've got it written here. So it's a distribution of possible responses given a prompt text under the current parameters.
Right, okay.
Of the model.
So yeah, I'm just trying to work out like how you do that with tokens. Because like I can understand that you'd have maybe you can compare like the first token, the probability distribution over the first token. But then how would you then expand that to like?
Yeah, so they also, it's a little bit later, but they don't do any kind of optimizations at the token level. It's always at the response level. So they do something called, I think, I don't know if I included it in this actually, to be fair. So it's called Singular Bandit, I think. Let me just find it here. It's called a bandit setting. So the idea is that you don't calculate any of the RL stuff on individual prompt probabilities. You just take the response as a singular whole, and so you're doing. So instead of like normally in RL, you would have like a set of states and action pairs, kind of like. Instead, with this stuff, you just treat it as a singular action. So the singular action is the response, and you extract away any of the sequential modeling. But yeah, then again, still, it's not super clear how exactly they how you take the set of distributions, of possible responses.
Yeah.
But yeah, this stuff, it gets pretty meaty pretty quickly, so I'm just gonna jump over this. But I'll
Sorry.
Yeah.
Sorry to interject. So I'm not too familiar with RLHF, but if it is a bandit problem, then rather than having a singular action, it just has no state. So it has multiple actions. The idea is like a bandit problem as being like a wait, am I? Yeah, like where you can pull various levers. So you have one state, and so that's it's kind of like you have multiple actions that you can take. It's just that you're not then that's no sequential component that you then moving to another state.
Yeah, so the way they describe it is as a bandit setting. So I don't know if that's slightly different from like a multi-arm bandit framework, but they essentially say there's no sequential action modeling. Everything, the generation of the response is treated as a single action to generate this response, or to generate a different response, rather than a sequence of generating this token, this token, this token as different actions.
Yeah. No, so I guess the way that they mean it here is the full response is generated, but then how do you then turn that response into a probability that you can compare against? How would that work? Because basically if you change just the initial token or one token, the whole probability distribution is going to change. If you see what I mean.
Yeah. I think it's the probability of generating that response under both policies.
Oh, right. Okay.
So what is the probability? So given this response, what's the probability?
Then how would you work that out?
I don't know. The only way I can think would be super computationally expensive.
Yeah.
But I mean,
I guess. Yeah.
And you just multiply that together or log it and add it, and then that's the probability of generating that response under that policy. And you just compare that. Okay. Can you see my screen? I don't know. Is it showing? Yeah. Cool. So yeah, that must be how you do it. Cool. Okay. So I'm gonna have to really go quickly through this because there's a lot of other stuff, and this is all RLHS stuff that I'm not super. A lot of it just gets quite heavy quite quickly. But there's some other stuff to do with attention, which is much more up my alley. Anyway, okay. So what they do is they are one of the critical things they say to the RLHF infrastructure is to use this leave one out estimator, and it measures the response of measures the quality of a response against all other responses to the same prompt. So the advanced response Y is the difference between its reward and the mean reward of all other responses. And this is another thing that I was hoping Callum might be able to shine some light on, but I'm not 100% sure. So they say this is very critical. This idea that when you calculate this advantage, you exclude the original. So if you can read the equation, so for response Y I, you exclude that from the average, and you just calculate an average over all other responses. Apparently, this is something that's super, super important to have stable training. Conceptually, I'm not sure fully if I understand why. I don't know if Callum maybe or someone else that's familiar with RLHF kind of understands why this leaving the current. Yeah. So Callum.
The leave one out thing, I'm not too familiar with in RL context, but I remember we learned in one of our courses, and maybe PMR. I don't know if you remember, Ocean. Or am I being mistaken? No.
I don't remember it from PMR, but
I don't remember.
Or maybe
reading it
I don't
now.
know. I might have seen it in my dissertation, or Okay, I haven't worked with that in a while, so I can't really comment.
Yeah, so I did a lot of reading, but was not super satisfied with any of the responses I found so far. But apparently, the removing of this yi of the response yi from the average significantly reduces the bias within the model and prevents overfitting. I think I don't know. It's something I need to dive into a little bit more. But I guess conceptually, if you're you don't want to evaluate, you don't want to weight that average using the current thing you're evaluating against. Cool. Okay, so this I'm just going to glide through very quickly, but another aspect to this algorithm is they use mirror descent to update the policy rather than updating it in parameter space. So the idea is you have the parameters, you map them to a another space that has some properties, you can exploit some geometric properties of the task, do your parameter updates in that space, and then map back to the original parameter space. Mirror descent is very, very mathsy and very heavy. I don't want to dive into it, but it's something I'm going to flesh out a lot more in my blog post. But this is also something that they found to be very useful to have stable training. Mirror descent also allows you to have this trust region, which is like kind of, you can define a region where you don't want the parameter update to go outside of this region, and that's what they kind of use to penalize the model from going too far away from the original policy. Cool. Okay, that's all the RLHS stuff. That was the heavy stuff. And now moving on to, so kind of we're at the stage now where you have a model, you've pre-trained it, now you've done post-training, and it's able to follow instructions, it's able to kind of align with what you want to use the model for inference time. Now, I'm going to go through some of the optimizations they've done to get these models to run on device. So a 3 billion parameter LLM is still a huge, has a huge memory footprint. One of the cool ones they use here is group query attention. I'm not sure if anyone's familiar with that. I hadn't heard of it before, but it's quite commonly used in smaller LLMs. And group query attention, I assume everyone's familiar with standard self-attention. This idea where you kind of project your tokens, your inputs to query key value, and then you kind of weight, you update every element of the sequence based on the other elements within that sequence. It's a great calculation. It's kind of literally powered the whole AI boom, just this one like self-attention feature. And usually this is implemented in a multi-head attention framework. So the idea is that you have multiple heads which are each calculating their attention scores separately. And this works very, very well. It's very good for performance. You can parallelize a lot of the operations, but the memory is very, very expensive. So for each input, you're projecting it to H queries, keys, values, where H is a hyperparameter where you can determine how many heads you want to do this calculation within. But you end up with each of your self-attention blocks having a huge memory footprint, especially if you have an LLM that has many, many self-attention blocks. And then memory bandwidth really becomes a bottleneck here. So there are solutions though. One of the extremes is multi-query attention. The idea here is that you want to remove the some of the key value pairs or just reduce them, and you take a hit to performance, but you get massive query speedups. So what you do is you project each of your tokens to a different query for H number of heads, but your keys and values, you only ever have one key and value at each stage. And this is really, really good at speeding up model performance, especially if you consider inference. For every token, you need to recalculate all of these. So your chain becomes really, really, for long answers, you're generating huge amounts of tokens. So this is a huge performance speed up. However, the quality of the model deteriorates a lot. So you do take a performance here. I've got some graphs later that kind of show this. So what group query attention is it's an interpolation between both of these extremes. So you have multi-head attention, which is great. It's super performant, but it requires a lot of memory. You have multi-query attention, which only has one key value pair for each head, for each token, but its performance goes down. What you can do with GQA is you divide your queries into G groups, and each of these groups gets its own key value pair. And you can obviously G as a hyperparameter you can decide on. And what this does is in the GQA framework, where you have G groups, multi-head attention would be GQA with H groups, so whatever number of heads, so multi-head, like GQA with 64 heads, and then multi-query attention is GQA with one group, and then I think the figures just kind of demonstrate it better. Cool. Okay. So this is what it looks like. So if you have multi-query attention here, which is the yellow dotted line. So obviously the time to generate a sample, generation of tokens, is very fast. But then you have multi-head attention up here, which is the time to generate samples is very low. The blue line is like an interpolation where you're kind of tweaking the number of groups. And then you can see the performance. GQA really hits a really nice sweet spot of minimizing the time to generate a token. So this means your generations are very, very, very fast, and the memory footprint of loading all these key value pairs into memory is much, much less. And you are able to pretty much maintain the same performance. So I think GQA is pretty much widely used now in smaller LLMs because it's such a nice. It gives you such fine-grained control of the trade-off, and you can really tweak it. They don't specify what kind of. I don't think they specify the exact number of groups they use, but they deviate between different layers of the model. Callum.
Oh, sorry.
Yeah, and David.
Sorry, I was a bit confused.
Okay,
So,
go ahead.
You're probably gonna ask the same question. Go for it.
No, okay, you go.
Come on, guys.
This is so cute. Stop. I'm just a bit confused by this graph because it seems like multi-head attention there has the longest time per sample.
Yeah.
Okay, cool. That makes sense. Sorry. But the quality is the highest. No, wait.
Yeah. So the time per sample is higher because the memory overhead of loading in all the matrices in and out of memory. Because
yes.
You can parallelize some of the stuff.
Right.
But the bottleneck they really try to fix is where you have your memory bandwidth, where the loading of all your matrices is a problem.
Yeah. Getting onto your accelerator actually is the challenge.
Yeah, which is actually what a lot of like self-attention speed ups look at now. Is just about the memory optimization in the GPU. It's not so much about the calculation or the implementation. It's a lot of like flash attention, all this sort of stuff. It's all about optimizing like GPU loading and
Super interesting. Cool. Thanks.
David.
Yeah, my question is, when do you have to choose the number of heads? Can you have multiple versions of the model with like, maybe if you go to the previous slide, that'll be better visible, right? Like there are, like you can have, here you have K1, K2, K3 matrices, but if you decide just having two, you would have only K1, K2, and they would be different matrices in this case, or like the mappings that are going to that. Are you sharing this information? Like which time do you choose the number of heads? Because like then perhaps you can decide like a trade-off at inference time, I now have more, memory available, so I can use like better, like more groups, right? Or they would be less groups, basically, right?
Yeah, so they show that one of the big parts of this paper that they also highlight, which isn't super relevant to this, is you can adapt multi-head models trained in a multi-head framework into a group query framework. So this idea is if you have a pre-trained model that's trained with just normal multi-head attention, maybe 64 heads here, what you can do is you can actually, if you want to turn that 64 into 32, you can then just do mean pooling between two, and then you end up with a model that has the performance does degrade a fair amount, but if you just do a small amount of fine tuning, you immediately get the performance much, much back. So you can do it. You can just do some pooling to reduce it, but usually I think all this in the paper, they really specify that you should do some fine tuning to really tweak the model and get it back into a good state where it's used to using that number of heads.
Okay, yeah. So then at the inference time, basically you can make a trade-off between the performance and speed.
Yeah, I don't know if you can really do it at inference. I guess you technically could. I don't think it's actually done in practice, because if you're if you're in inference and you're using 16 heads and you're saying like, okay, I only want to use 2, you're doing mean pooling over 8 matrices, I think the quality of the model will be pretty poor. But you can definitely create flavors of the same model very efficiently with different versions. Cool. So yeah, this is a very cool component to how they really address some of the memory issues that they would normally have with trying to run this sort of stuff on iPhones. Okay, so now we have 2 more sections. One is all about adapters and LoRa, which I know some of you guys are familiar with. It's pretty cool stuff. And then we're going to go into quantization. So first, what we have now, I guess the stage we're at is this part here isn't really part of the model training. It's more like an architecture decision you make before the pre-training, but I wanted to include it here. So now we have a model that's efficient in its memory usage. It's done pre-training and post-training, and now what we're looking to do is try to take this the singular foundation model we have and use it to power products. So what they find is that the AFM on-device model is a strong baseline model, but by using adapters, they can get the model to have best-in-class performance across many, many different tasks. The same fundamental model can be adapted very easily. And what you do is you make use of these things called adapters, which are essentially just small neural network modules that you plug into. And what they do is they plug it into every single linear layer of the model. They have so in self-attention and just outside of self-attention blocks. They plug in this neural network module, and whenever they're doing fine-tuning, they only fine-tune the weights of that module. The underlying weights of the model, of the foundation model, are never updated. And what that looks like is you essentially have your original weights here, which are the weights after post-training, and you add this delta W, which is it's just these two matrices times together. And what they found is that you can their trade-off came rank 16 matrices. So that would be, given that the hidden dimension of the model, I think, is 3072. The shapes of A and B would be this. And then what you do is you just fine-tune A and B during training, leave W as it is. And from this, they found that the memory footprint of each of the adapters was tens of megabytes. So very, very small compared to the underlying foundation model. Yes, Ben?
How many layers? Is this done at a layer level, or is this done when the token's been produced?
So they have 26 layers, and it's done in any linear layer, either within self-attention blocks, so the key query matrices, or also just linear layers in the normal model. So you can see here, this linear layer would be adapted here, and it's done
all the way down, or
every single layer.
All right. Okay.
Cool. So yeah, so through adapters, this is so we'll come back to adapters actually in a second. What we can jump to now is compression. So the idea is that we have this base model. We have a series of adapters. Each adapter is designed for a different task, and they use the adapters to specialize the model for different tasks. And now the big problem is that the model is good, but it's also very big. It's trained with float 32 and float 16. So I did a quick calculation. So Llama's 3.1 405 billion memory footprint at different quantization data types would produce vastly different model sizes. So the idea is that you train most neural networks. I think it's very common to train with some sort of 16-bit bits per weight, slightly structured in different ways depending on exactly how you're storing your floating points. And what you want to do now is you want to try and maintain the quality of the model, but reduce the number of bits you need to store each weight. And this is quantization. So after post-training, we want to compress the model, going from 16 bits, and they managed to compress the model to less than 4 bits, whilst also maintaining, I've got a table a little bit later, but they maintain really, really strong performance, whilst vastly reducing model size. So the way that the weights are quantized is they take a weight matrix, like up here, they split it into blocks, where each block is just kind of a square section of the matrix. It can be different sizes. And then within each block, they run k-means clustering, and they take the raw values of the weights. They learn centroids within each block, and they assign each weight value to whatever centroid is closest to. So kind of standard k-means clustering, and that's how they determine what value each weight value gets changed to. And then the idea is that the smaller your quantization blocks are, the higher performance, the better the model will be, but the less memory you're kind of saving, because it means you can kind of if you learn quantization on a block that only has 16 weights in, you can learn each centroid will be aligned with one of the weights, but then you have to store that information at inference time. So yeah, they say they use up to 100K size of blocks. So when you quantize the model, you end up with a significant performance hit. So what you're doing is you're taking all the weights it's used to, you're slightly changing them all slightly, and now impact is obviously compounded through the model, and you end up losing a fair amount of performance. What they found is they can use these accuracy recovery adapters, so essentially LoRa adapters. So they quantize the model, leave it as it is, add these adapters in, which the adapters are stored in 16-bit parameter space. And by using these adapters, they're able to rapidly recover the majority of the model loss. And what they show that they can actually go down to 3.5 bits per weight and still have very good performance, but apparently around 3.7 is when they hit their memory target. So you might be wondering how do you have half a bit or a seventh of a bit? And what they do is they've built a robust framework that allows them to identify which layers of the model are the most important. And the most important layers they quantize to 4 bits. Layers that they determine to have less importance and less impact on the output of the model go down to 2 bits. And that's how you kind of get this interpolation that you end up with 3.7 bits here. And here are like the raw values that of the performance able to recover. And cool. Okay, that's it. That's the whole presentation. Are there any questions anyone want me to get back to on the slides? I know there's quite a lot of information.
I had a question that's coming back to RLHF because you were talking about RLHF and DPO, and did in the paper mention why they are still doing RLHF compared to DPO? As like in RLHF, you need to create a reward model, which is quite complicated, whereas in the DPO, you're basically directly optimizing the policy of the network, which should be a bit straightforward and like easily done. So do they compare these two methods as they're doing the voting at the end?
Do they present like a comparison?
Yeah, exactly. So it's like no,
really.
like OpenAI doesn't speak about this almost at all. Meta hasn't. I didn't read the Llama paper yet, but like I wonder why do you still do RLHF if you can like they basically create like a binary cross entropy optimization in DPO, and then you don't have to train the whole like reward model. So what's the advantage?
So all of it, DPO, IPO, rejection sampling is all touched on very briefly. They don't really explain too much, and they say that these are only 3 of the models of the. So these are the methods they use to train the committee, not to necessarily optimize the actual model weights. So the committee is there to distill their information in, and not necessarily as a training mechanism. They use supervised fine tuning of the generated data set from DPO, but yeah, unfortunately, they don't have these kind of like fine grained comparisons in their evaluation section. They just have a lot of stuff where we compared to GPT-4 and we got 97% on this benchmark, but they don't really do like ablation studies or super like in-depth stuff like this, unfortunately. Neil.
Yeah, thanks, Josh. You can bear in mind that I probably understood like 3% of what you just said, but I'm thinking more about like how do I put this in the hands of a user? And one of the things I understand about Apple Intelligence is a bit more differentiated is the fact that they're essentially doing what Rabbit were trying to do with their large action model. So rather than just like ask a question, get some text in response, or have like a voice assistant speak back to you, it's actually calling APIs and all the different apps you have installed on your phone. So can you talk, did the paper allude to like how they're doing this, the challenges associated with this, or have you actually already explained that? And I just understood none of what you were saying.
So they do allude to this a little bit. So it's all done through tool use, and this is done at the post training stage. So what they'll do is they'll encourage that's where they instill the information of like how the model knows which tools to use at different times. I think they have a huge quantity of custom tools that they've built in that all kind of work with the Apple ecosystem. So through the model, you're able to set an alarm, do these other things. These are all structured as like tool use tasks and offloading information to on server models. Also, they don't specifically say, but I'd assume that's done through a tool use scenario. And one of the big things they actually focus on with their adapters is their adapters that kind of allow the model to update itself to depending on the task that the user needs to perform. Those adapters are all hot swappable. So as you're kind of talking to the same model, it can in real time kind of change the adapters it's using, which kind of changes the behavior it has. And all of the offloading of information or kind of interacting with APIs will happen through tool use.
Got it. Do you mind if I just ask one quick follow-up? How does that tool use work? So like, do these apps, when they now
push updates, or they just first of all submit an application to the App Store? Do they have to make their APIs accessible to Apple? Like, how does that work? I think Rabbit, we're actually trying to like scrape the UI and interact with it like a human would, but like, how do they interact with third-party APIs?
Yeah, so I'm not 100% sure exactly with third party. I'd assume there's some SDK that Apple provide, which is a framework that developers can use. The way tool use normally works is the model can output kind of direct text, or it can output some sort of structured output that specifies which kind of tool it wants to use. And then it expects some sort of information back, and then it will go back into the standard autoregressive kind of generation of text. But like this is it's pretty common like stuff that like Claude and GPT-4. This is kind of how they instill their actions that are not just text outputs. You can and you can use this. So I would assume that they're probably building a very comprehensive SDK around this, so developers can directly access this. I'm not sure exactly how that's implemented, but it would be quite interesting actually to check it out. David, did you have something to add on this? Do you have a better idea?
No, you're correct. I think it'll be everything about the adapters with LoRa. I was just curious, like, did they mention in the report, like, how many LoRa adapters they're building, like, which ballpark, like, because they'll be for each task and each application, but like each role, and is going to be granular and granular, I guess, in the future for like each.
I think
Well,
it's
putting on privacy, right? So I will have my LoRa adapter for my email, right?
Yeah. So I think it's very granular. So, for example, they one of the things they offer is summarization or tone adjustment. So this idea that if I write an email and I'm super angry at my colleague for doing something bad, you write a really angry email, and then what you can do is you can highlight that and get it to write it more friendly or more work appropriate. I would think that all of these different tones themselves are different adapters. They have one figure in the paper that kind of alludes to this, but they never really specify it. But there's at least 9 adapters, because they show 9 as an example in that figure with a ... But they have a different they show different adapters for the different tone types that they want to optimize for. And they do mention that they put a lot of time into building a robust framework for deploying more adapters, updating adapters, I think they're kind of like heavily leaning into like the adapter as a solution to specializing for different tasks in the future, without having to update like the foundation model. So I would assume a lot of adapters probably going to use it. Cool. Okay. Did anyone else have anything they wanted to go through and discuss?
Yeah, thanks, Josh, for the presentation. Very interesting.
I
had a little thought. You mentioned these different models that then the reward function would choose which answers the best. How does that relate to mixtures of experts, and potentially can you combine both methods?
Yeah, so I'm not super. From my understanding, mixture of experts is when you kind of use multiple models within, you kind of chain them together. So GPT-4 was like a mixture of experts model where you have, I have no clue how many they use. I don't think anyone knows, but like you just have multiple models that you combine together, and you take the output of the one that's most preferred. So it's very similar to this, but it's just you're not. I think with mixture of experts, the goal is to kind of camouflage multiple models as a single big model. In this case here, you're just keeping the models separate, and each of them is generating a separate answer.
Okay. Well, it's a more broad question, but there was another paper lately by Meta about the Llama architecture 3.0, 3.1.
Yeah.
How come are like these big companies releasing these papers lately? Like, is it a trend? How do you see this happening?
Yeah. So I think OpenAI is quite famous now for not releasing any of this stuff anymore. Meta and Apple, I would say actually Apple has a really good open source reputation, from my understanding. A lot of the stuff they do a lot of like the software engineering stuff and the frameworks they build. I think more so than people know, they do open source a lot of their stuff, and they do have a really good wealth of papers. If you go to like the Apple research, machine learning research, they have like a dedicated website, and they have new papers coming out all the time. A paper of this magnitude, I don't know if people were super expecting it, something to go into this much detail where they really just specify the number of layers in the model and all that sort of stuff. I haven't read the Llama paper yet, but I know Rory is reading it, and he also works at Apple, so he might be a good person to answer both of these things if you want to dive in, Rory.
Yeah, well, I don't have the background that everyone else seems to have on ML in this call, and I have been reading the Llama paper. I think from an open source perspective, though, like Apple isn't that big on open sourcing, but within the ML community, in order to attract talent, you've kind of got to allow people to open source and continue their career outside and their research status. So I think that's a massive part. So you'll see a lot of ML stuff, and like Josh said, like a dedicated research part of Apple's kind of public website where you can view a lot of this. So I'd dive into it if you get the chance, but I haven't had the opportunity yet.
Yeah, I would say actually Apple. I think if people know Ian Goodfellow, I think that was kind of a famous exit for them because he was he was a high like talent acquisition for Apple, and I think he was just writing pattern after pattern after pattern, and not getting to write as many papers as he wanted, and he left the company for DeepMind. So I guess maybe Apple's trying to rectify that and try and lean heavily more into the ML side. Callum, I see you've got your hand up.
Yeah, just on this point, I mean, obviously there are all sorts of incentives around these things, but I think a really insightful perspective I heard once, Zuckerberg was talking about it, and he kind of said that like if they if they spend, I don't know, $10 billion doing something, and they put it out into the community, and the community makes it better. Now, like you can see, everyone's building on Llama, right?
Yeah,
Because they're like, firstly, all the universities are like, finally, there's something that we can actually use and access. And then a bunch of spin-off companies as well. They're going to make it better. And if they can, you know, make it 1% more efficient or 5% more efficient, or improve the architecture in some way, because Facebook's just operating at such a scale, that translates to easily covering the cost. And so that's Zuckerberg's perspective, purely on a monetary thing. And then my perspective, particularly just around the Meta thing, is that they went through really bad PR around data privacy in, you know, maybe the 2016 election, and there was that ongoing stuff for quite a while. And with OpenAI and DeepMind increasingly closing their ecosystems, I think Meta just saw an opportunity that they can actually do a PR 180. And that's exactly what they've done, right? Like no one is talking about Cambridge Analytica anymore because everyone's talking about Llama. And so Zuckerberg himself has gone through a big rebrand, and he kind of has owned it, but we kind of forget about how much of a kind of a weird dude he is, and how strange he was, like, you know, a couple of years ago. And so I think that there's huge PR value in that. And suddenly working at Meta or the products from Meta, I think people just in the public eye, and I'm speaking generally now, like I think a little bit less scrutinizing it less because AI researchers are just so excited about it. And yeah, there's a little 2002 article that David just shared about open source. And I think it's particularly true now in the era of these like incredibly large models because, you know, people have to kind of be building on other people's work. And so if you can get people locked into your ecosystem, you kind of, that's kind of the plan.
Yeah, I think as well, I think Zuck touched on the same point a few times. He's done a lot of interviews recently, but he frequently says that a big thing that hurt Facebook and Meta was the fact that they didn't own any hardware. They were kind of an application running on Apple and Google hardware, and they were very much at the mercy and I guess not so merciful action where like Apple at any point you just cut off all the app tracking that just massively like tanked Meta's revenue. So then they really struggled with the fact that there was no open platform that kind of allowed them to not be so dependent on these huge players. So from my understanding as well, they really want to try and make sure the AI landscape isn't like that. So by releasing these models, they're really trying to influence the landscape to be much more open source and not to have these not to be overly reliant on GPT-4 and Gemini, which I guess, interestingly enough, Apple's kind of like relying on GPT-4 a little bit, and I'm not sure what that kind of deal looks like, but I'd assume it's not a position they're happy to be in, where they're kind of relying on another company to do all of that. So I think they're really trying to make sure the AI landscape remains open because it works much better for them if all these things are open. Cool. Okay, I'm conscious of time. We can maybe wrap up there unless anyone else has anything they want to say or go through.
I've got a question for you, Josh. Sorry, Maria. What's your big prediction? How does this all come? What's Apple Intelligence in 5 years' time?
Yeah, so I can go quickly, but I think honestly, I think it's actually quite impressive what they've done. I think there was a lot of noise around like GPT-4s, Gemini, all these things coming out. I think when Apple announced, almost the ML community was like a little bit disappointed. This idea that they were offloading stuff to GPT-4 was a huge headline and almost like painted as like an embarrassment for a company of this size to not like given the talent they have, not be able to do this. But I really think that this could become one of the most impactful models that the majority of people use on a day-to-day basis. Apple have like the market share of most of us in this call have iPhones in our pockets. I'm using MacBook Pro. Like they just have such wide reach that if they just build these tools, they build it well, they build it into their devices. These tools will become the most used tools on the planet. So I think they're kind of starting on the back foot a little bit in that they don't have frontier models, but I think in terms of actual like, application of useful models, the utilization will be very high. Callum and Maria, I'll let you guys fight it out.
So Maria is saying that I shouldn't ask this question, but I was just going to add that I think Apple's really well positioned because of their just control of the like full stack software to hardware. And we saw for quite a few years like Apple Silicon not actually really being used for like we had all these like ML accelerators and stuff, but like not really being used. But I think in conjunction with this kind of data privacy movement, Apple's just so well positioned to like now actually get onto those on-device stuff and tick both of those boxes. So it's a pretty interesting. I'm pretty bullish on them. After the tech meltdown this week, though, so that'll start.
Yeah.
Sorry, Maria, for asking that question. Adding that into.
I just wanted to take a screenshot with everyone. Arjan, come back to the camera. If everyone is okay with this only.
Yeah, I'd assume so.
Cool, 1 second.
Arjan, you got such an imposing figure. Like you got the light behind you.
I don't know.
The golden box.
Can you look normal? Okay, ready? Smile. Got it.
Okay, cool. Thanks everyone for joining.
Thanks, guys.